Hello students, how are you all? Today we are going to solve numericals based on moving charges and magnetism chapter. Okay, so this chapter every student used to feel somewhat difficult. I would like to try to make it as easy. So try to understand the approach that I am going to do here and try to follow the pattern that I am following. So if you feel it is easy, then follow it. Otherwise, your own plan. Okay, let's get started. The very first question is based on magnetic force. A metallic rod of mass per unit length 0.5 kg per meter is lying horizontally on a smooth inclined plane which makes an angle 30 degrees with the horizontal. Okay, let me draw the diagram. Guys, observe this diagram. So an inclined surface is there. On the inclined surface, a metallic rod is placed whose mass per unit length is given, that is m by L ratio, which is equal to 0.5 kg per meter, is placed horizontal on a smooth inclined plane which makes an angle 30 degrees with the horizontal. Okay, the rod is allowed to slide down by flowing a current through it when a magnetic field of induction 0.25 Tesla is acting on it in the vertical direction. Okay, super. Let me represent the direction of magnetic field also. So magnetic field is directed vertically upward and this rod is allowed to move on the inclined surface like this. This is the direction of motion of the rod and it is represented as V here. Okay, so if you use Fleming's right hand rule, you can find out the direction of current flowing through the conductor. So what is the procedure to find out current flowing through the conductor? So an EMF induces and the current flows through it if it cuts the magnetic field lines, right? So this conductor is moving in a magnetic field, then EMF induces in it. If it is a closed surface, then current flows through it. This is the process that we know. Okay, what is Fleming's left hand rule? So this is what Fleming's right hand rule. Forefinger indicate direction of magnetic field, thumb indicate direction of motion of the conductor, and middle finger indicates the direction of current. If you use that rule, try to use that rule on this plane, then you are going to get direction of current in this direction. So this is how you are going to get current. Okay, so if this is the direction of current flowing through the conductor, so I'm just showing this diagram. It's just only front view of this. So just observe here, this is how the conductor is placed on the inclined surface. I'm just showing you only front view. This is where conductor, and what's the direction of current? Direction of current is out of the board like this. And what's the direction of magnetic field? Is upward. This is magnetic field direction, and the velocity of the conductor is like this. This is how velocity is represented. Now, whenever a current carrying conductor is placed in magnetic field, a force acts on it, right? So right now it is carrying current I. So because of induced EMF. Now this current carrying conductor is placed in magnetic field. If a current carrying conductor is placed in a magnetic field, a force will act on it. How to find out direction of force? For that we have right hand palm rule. So this is what right hand palm rule is. 4 fingers, that is forefinger, middle finger, ring finger and a small finger. All these 4 fingers represents the direction of magnetic field. Thumb indicate direction of motion of a positive charge or current, both are same only. And open palm indicates direction of force acting on it. If you just use this rule, you are going to get direction of force acting on this conductor towards left. This is the magnetic force, and we know the formula for magnetic force acting on a current carrying conductor, that is Fm is equal to BIL. BIL sin theta will be there. So actual in terms of vector form, it is actually represented is as L bar cross B bars. This is the way of representation. Here theta is 90 degrees. What's the meaning of theta? Angle between length of the conductor and magnetic field. Here it is 90 degrees. So it's going to be BIL. This is the magnetic force acting on that conductor. Okay. What is the question they're asking? So we have to find out the current flowing in the rod to keep it stationary. Okay. So we have to find out the magnitude of current so that this is going to be at stationary position. So meaning of stationary, it is at rest position. There are two forces acts on it. Let me divide weight of the body into two components. Let's say this is M30 and horizontal component of mg on the inclined surface is always mg sine theta, which is mg sine 30. So if this is 30, this is also 30. Let's divide this also into two components. Force is also divided into two components here, which is Fm cos 30. So as they said, to maintain to keep it is at stationary. So these forces which are acting on this rod, which are opposite direction, they must be equal in magnitude, opposite in direction. So that means I just have to equate them. That is for stationary condition is F net acting on the system is 0. F net acting on the system in the sense Fm cos 30 must be equal to mg sine 30. Okay, so let's equate it. So what is Fm? BIL cos 30 is root 3 by 2, which is equal to m into g sine 30 1 by 2. This 2 will get cancelled. So next from this I is equal to m by L into g into 1 by b. So m by L is already given, that is mass per unit length, that is 0.25 kg per meter. So this complete value is given m by L, which is 0.5, g is 10, magnetic field is 0.25. So this can be replaced as 5 into 100 by 25. We forgot root 3 value. So here you are going to get root 3 in addition to it. Okay. Okay, 1 by root 3. So they gave g value, they didn't give. If they didn't give, we have to consider 9.8. For calculation purpose, I took it as 10 itself. You can take 9.8 also. If you take 9.8, you are going to get exact answer. So from this, if you substitute all these values, 25 4 5 4 is 20 by 1 by root 3 is 0.577. So approximately you are going to get answer as 11.32. Your answer may be different if you do this calculation, because so whatever the option is may be different than this, because I took g value as 10 here. If you take 9.8 exactly, you are going to get this answer, that is 11.8. Understood? Let's move on to the next question. When a proton is released from rest in a room, it starts with an acceleration a0 towards west. Okay. Question number 2. So I'm releasing a proton. Proton is of a positive charge. If I release it, it moves towards west. Let's say this is east direction and this is west. Now this proton is accelerating towards west. What does it means? Definitely electric field should be from east to west, right? Whenever a positive charge is placed in a electric field, it always moves in the direction of electric field or opposite direction of electric field. It always moves in the direction of electric field. That's why I just represented direction of electric field is from east to west, just because charge is accelerating towards left, that is towards west direction. Electric field is from east to west, because positive charge always moves in the direction of electric field. Now it is accelerating with an acceleration a naught. Okay. Now what's the question they're asking? The electric and magnetic field. So first of all, let's talk about this. This is case 1. In this case 1, as electron is accelerating towards left, so we know the procedure. So what's the formula for force acting on a charge placed in electric field? That is Q into E. And what about acceleration? Acceleration is equal to Fe, electric force divided by mass of that charged particle. Electric force is Q into E divided by M. So where A is A naught, from this what's the magnitude of electric field? Electric field is equal to M into A naught divided by charge of the proton. Charge of the proton, I'm going to replace it with E. So here, as it is a proton, you can write down it as E plus here. So which option matches? And what is the direction of electric field here? Here towards west or towards east? Electric field is towards west. So we have only one option. Sorry, we have two options, option C and option D. We have to cross check which is correct. Okay, super. So first case completed. Let's observe case 2. Okay, what's case 2? When it is projected towards north with a speed v naught, it moves with an acceleration 3a naught towards west. Okay, then electric field, and okay, so super. Already you know that direction of electric field is towards left. Okay, now this proton is being projected with a velocity v naught towards north direction. This is north, east, west. So when this proton is projected with a velocity v naught towards north direction, it is getting accelerated towards west. Okay, then what is the meaning here? Magnetic field must be into the board here. So you can use that rule called as right hand palm rule. Whenever a positive charge is moving in a magnetic field, a force acts on it, and the direction of force can be found by using right hand palm rule. 4 fingers indicate direction of magnetic field. Thumb indicates direction of motion of positive charge. Open palm indicates direction of force acts on it. So because of that force is towards left, that is towards west now. So because of that force, this charge is being accelerated towards left with an acceleration. What's the acceleration diagram? 3a naught. Here this is total acceleration because of both already electric field is present towards left. Because of presence of magnetic field, now this charge is getting accelerated by 3a naught. That means one acceleration is due to electric field, another acceleration is due to magnetic field. So this is the direction of magnetic field. Is it down or up with respect to that paper? So magnetic field is in downward direction. Now we know the formula for force. What's the formula for force acting on a charge placed in or moving in a magnetic field? It's QVB, right? It's VB naught, and F is equal to QVB, and acceleration is, this is a magnetic force. Acceleration is F m divided by mass, which is QV naught B divided by m. This acceleration is equal to 2 times of A naught. It is produced by magnetic field. From this, what's magnetic field? 2a naught into m divided by charge. I'm going to replace it with proton representation, E into v naught. Which option? Option D is the correct match for this question. Understood? So try to understand. It's a deep understanding of the question. We have to apply several rules to understand this. Hope you understood. If not, go through it again. Question number 3. A long straight wire carries a certain current and produces a magnetic field 2 into 10 power minus 4 Weber per meter square at a perpendicular distance 5 centimeter from the wire. Okay, super. Let me draw the diagram. Observe this diagram. So it is carrying, this conductor is carrying a current. They said a long straight wire, right? So whenever they said a long straight wire, it is of infinite length. So we know the formula for magnetic field due to a infinite straight wire, that is mu naught I by 2 pi r, where r is perpendicular distance from the long straight wire. There are two different ways to find out the direction of the magnetic field, I mean right side or left side of the current carrying direction. So we have a rule for that, that is right hand thumb rule. Right hand thumb rule. So according to this rule, this is what right hand thumb rule is. Thumb indicates direction of current and curled fingers indicate direction of magnetic field. If you use that rule, so right side of this current magnetic field is going to be into the board, left side is going to be out of the board. How can I decide whether it is right side or left side? Always with respect to current direction. With respect to current direction only, I can decide whether it is going to be right side of the conductor or left side of the conductor, not with respect to original directions. Okay, hope you understand. In this case, direction of magnetic field is into the board at a distance 5 centimeter perpendicular to the conductor. What did they say? An electron is situated 5 centimeter from the wire, moves with a velocity 10 power 7 meter per second towards the wire. Okay, super. So now at this position, electron is situated. This is moving with a velocity 10 power 7 meter per second towards the wire along perpendicular to it. The question they are asking is force experienced by this electron at this position. The formula for force is QVB. I'm not using sin theta because theta is 90 degrees. Theta is the perpendicular, what do you call it? Theta is the perpendicular distance, angle between velocity and magnetic field, right? Magnetic field is into the board, velocity is towards left, angle between them is 90 degrees. So what's the charge of an electron? 1.6 into 10 power minus 19, velocity is 10 power 7. And what about magnetic field? 2 into 10 power minus 4. So if we solve this, we are going to get answer as 16 2s are 3.2. I mean 1.6 into 2. 10 power minus 19 into 10 power 7 is 10 power minus 12 into 10 power minus 4 is 10 power minus 6 newtons. This is the answer. Option B is the correct answer. Got it? So questions are lengthy, so to read it, but to answer they are very easy only. Have some patience and try to solve all of them. Okay, let me read out this question number 4. A uniform electric field and uniform magnetic field are acting along the same direction in a certain region. Okay, this is how it is. So both are moving, both are acting along the same direction. If an electron is projected in the region such that velocity is pointed along the direction of fields. Okay, electron is projected such that its velocity is in the direction of these fields. Okay, super. This is velocity. When charge is initially having some velocity and it is moving in the direction of fields. Superb. So what's the question they're asking? Okay, pointed along the direction. Then the electron, okay, first option, will turn towards right direction. So first of all, let me decide what's happened here. See, one thing I can decide, whenever velocity and magnetic field both are in same direction, magnetic force acting on the charge is 0. Magnetic force is equal to 0. Reason is magnetic force formula is Q into V vector cross B vector. If angle between these two is 0, sin 0, 0, so magnetic force acting on the charge is 0. If V bar and B bar are in the same direction or opposite direction, answer is going to be 0. There is no magnetic force. But Whenever a charged particle, whether it is a positive charge or negative charge does not matter, whenever those charged particles are in uniform electric field, they will accelerate. Positive charge accelerates in the direction of electric field, negative charge accelerates in the opposite direction of electric field. So this is the direction of electric force acts on the negative charge. Now if you observe, force and velocity both are in opposite direction. So acceleration is going to be negative or positive? Acceleration is negative. If acceleration is negative, then what happens to velocity? Decreases or increases? Decreases. Which option is correct? Option B is correct. Check out, this is the information. Understood? Let's move on to the next question. Question number 5. What's the question they are asking? The magnetic force acting on a charged particle of -2 microcoulomb in a magnetic field acting in y direction when the particle velocity is 2 I cap plus 3 j cap into 10 power 6 meter per second. Okay. Let me draw this. This is the given data that they have given. Now, we know the formula for magnetic force acting on a charge moving in a magnetic field, that is Q to V bar cross B bar. I already told you this formula is applicable for positive charge motion, right? Applicable for positive charge motion. I mean, to find out direction, it doesn't mean that we should not substitute a negative charge. We can apply it. Okay. To find out direction, generally I used to use only for a positive charge. That is a suitable rule. Okay. Instead of writing like this, let's keep it as simple. It is applicable for both, but the conditions are there. Okay. Okay. Now in this case, what is the procedure to find out cross product? So we know that method, right? Let's use that method and let me substitute those values. Its charge is -2 microcoulomb, -2 micro in the sense 10 power -6. Velocity is 2 I cap plus 3 j cap into 10 power 6 cross 2 j cap. Okay. So let's find out the cross product of these two. It's better to bring this 10 power 6 outside. So 10 power 6, 10 power -6 will get cancelled out. -2 into 2 into 2, 4. I cap cross j cap. I cap cross j cap is going to be k cap. Right? Are you guys following? And 3 into 2, 6, j cap cross j cap is going to be 0. No need to use that. So final answer is going to be -8 k cap or 8 newtons in -z direction. Check out which option matches. Option D is the correct answer for question number 5. Understood? Okay, let's move on to the next question. Question number 6. When a charged particle moving with a velocity v subjected to a magnetic field of induction B, the force on it is non-zero. Remember, the force on it is non-zero. This implies that, okay, so let's answer with the help of options itself. What's the general formula for magnetic force acting on a charge moving in a magnetic field? That is QVB sine theta, right? Where theta is angle between magnetic field and velocity of the charged particle. Okay, this is the formula that we are going to use to answer this. Let's observe first option. Angle between angle between them is either 0 or 180. So if you substitute theta is equal to 0 degrees or theta is equal to 180 degrees, see, angle between is, that's the meaning, not angle between 0 or 180. Be careful with the terminology. If you substitute theta value either 0 or 180 degrees, then you are going to get magnetic force is 0. So first option is not correct answer. We need non-zero force, right? Okay, let's move on to the next. Angle between is necessarily 90. Okay, if theta is equal to 90 degrees, then what about magnetic force? Is magnetic force is going to be QVB. Okay, accepted. But there are several other conditions also. Okay, let's cross check. So here it is non-zero. Okay, accepted. Let's observe another one. Angle between can have any value other than 90 degrees. Okay, so they're saying other than 90 degrees, it can be any value. Then I'm going to get non-zero. Okay, for example, if I substitute theta 180 or theta 0, then what's going to be magnetic force? Magnetic force is going to be 0, isn't it? They're saying angle between any value other than 90 degrees, if you substitute, you are going to get non-zero force. Is that true? No, it is not true. And observe option D. Angle between can have any value other than 0 or 180. So whether you are so if you substitute either 0 or 180, you are going to get answer as if magnetic force as 0. If I substitute 30 degrees, if I substitute 60 degrees or 120 degrees or 45 degrees or 90 degrees, in these cases will I get Fm is equal to 0? No, it is not equal to 0. So even for theta is equal to 90 degrees also, you are going to get non-zero force, but this is the suitable answer, perfectly suitable answer. That means if theta is other than 0 degrees or 180 degrees, in all the cases, then you are going to get Fm is non-zero. So which option is correct? Option D is the correct answer for this question. Question number 7. Let's solve this. A very long straight wire carries current I at the instant when a charge plus Q at a point P has velocity V as shown. The force on the charge is, okay. Just observe this question. They said a very long straight wire. What does it mean? Infinite length wire carries a current I. So if it is carrying current I, it is this point P right side of current direction or left side? Right side of current direction. It is always with respect to current direction. I told you earlier, if you want, you just go through the previous questions also. Okay, so here magnetic field direction is into the board. Charge is moving towards right. Use of right hand palm rule. 4 fingers indicate direction of motion of direction of magnetic field. Thumb indicates direction of motion of positive charge. Then definitely force acts on it is going to be along plus y axis. That is in which direction? Is it OY or along OY? I think it is along OY. Check out which option is correct. Option A is the correct answer. Understood? See, be careful. You just have to use this rule. So nothing to hesitate to use this rule. Just whenever I told you these rules, you just use them perfectly. Okay, right hand palm rule. Where is it? Here it is, right hand palm rule. 4 fingers indicate direction of magnetic field. Thumb indicates direction of motion of positive charge or current. Open palm indicates direction of force. If you use that, you are going to get the answer here. Understood? Is this magnetic force along y-axis or along x-axis? Along y-axis. So that's why it is from O to y direction. That's the force. Let's solve next question. A charge Q moves in a region where electric field and magnetic field both exist. Then the force is equal to this one, Lorentz force. So hope you know the meaning of Lorentz force. So Lorentz force is nothing but a vectorial sum of electric force and magnetic force acting on the charge. That is Fe plus Fm. So vectorial sum. Fe is Qe plus Fm is Q into velocity vector and magnetic field vector. This is the answer for question number 8. Understood? Okay, next question. Tesla is unit of magnetic field. Another one. It's a simple question. A charge moving with a velocity v in positive x direction is subjected to field of magnetic induction in negative x direction. As a result, the charge will. Okay, here it is. Velocity of the vector is in the direction of in the positive x direction, and magnetic field is in the negative x direction. What's the formula for magnetic force acting on a charge moving in a magnetic field? QVB sine theta, right? What's the value of theta here? It is 180. If it is 180, then what's the magnetic force? Magnetic force is 0. Is there any force acting on the particle? No. Now, what should we have to do? As magnetic force is 0, I think particle will move with the same velocity. There won't be any effect on its velocity. That means it remains unaffected. So option A is correct. Next, question number 11. Understood? A straight wire of length 0.5 meter and carrying a current of 1.2 ampere is placed in a uniform magnetic field of induction 2 Tesla. The magnetic field is perpendicular to the length of the wire. The force on the wire is. What's the formula for magnetic force acting on a current carrying conductor? That is I into L vector cross B vector, where L vector is displacement or not a distance. Displacement. Okay, so it represents that length of that conductor. So let me expand this. It is going to be BI L sine theta, and that's it. One more thing, magnetic field is perpendicular to the length, that is L bar and B bar are mutually perpendicular, so theta is going to be 90 degrees, sine 90 1. B value is 2 Tesla, current is 1.2 ampere, length of the conductor is 0.5 meter, and answer is going to be 1.2 Newton. Question number 11, which option? Option B is the correct answer. Got it? Let's move on to the next topic. Let's move on to the next question. Ionized hydrogen atoms and alpha particles with the same momenta enters perpendicular to a constant magnetic field B. The ratio of their radii of their paths RH and R alpha will be. Okay. So whenever a charged particle enters perpendicular to magnetic field, it undergoes a circular path, and formula for radius of that circular path is mv by qb. This is what you have to understand. When it is applicable? When a charged particle enters parallel to magnetic field or perpendicular to magnetic field? Perpendicular to magnetic field. If this charged particle is moving perpendicular to this magnetic field is into the board here, then this charged particle undergoes a circular path, and radius of this circular path is given over there. Got it? Hope you understand. Radius of the path, let's say it is smaller, and that smaller is given over there. Now what is the question they're asking? They said same momenta, meaning momentum is the same. This value is the same. And magnetic field is also same, right? Then R is inversely proportional to Q. I need ratio of RH by R alpha, right? Which is equal to Q alpha by QH. Charge of alpha particle is 2Q. Charge of hydrogen is Q. So it's going to be 1Q. Q will get cancelled. You are going to get answer as 2:1. Which option matches here? Option B is the correct answer. Understood? Okay, let's solve next question. Question number 13. A proton and an alpha particle both enter a region of uniform magnetic field B, moving at right angles to magnetic field. What kind of path that charged particles undergoes? Definitely circular path, because they are entering perpendicular to the magnetic field. Okay. If radius of the circular orbits for both the particles is equal, super, and the kinetic energy acquired by proton is 1 mega electron volt, the energy acquired by the alpha particle, super. There are a proton and alpha particle. Both are entering perpendicular to the magnetic field, proton and alpha particle. If both are entering perpendicular to magnetic field, so both will undergo a circular path. So what's the formula for radius of the circular path? R is equal to mv by qb. In terms of kinetic energy, this formula is, this is momentum, right? This momentum can be replaced as 2mke kinetic energy divided by qb. This is the general formula in terms of kinetic energy and radius. They said radius of both the charged particles is same and kinetic energy are different. Okay, so in this case, in this formula, try to observe which are constant here. R is constant, magnetic field is constant, mass and charge both are getting varied. So from this, let me write down the relation. Can I write down this as Q is directly proportional to root of m into kinetic energy, or else I can write down kinetic energy is proportional to Q square by m. Then what should we have to find out? Kinetic energy acquired by alpha particle. So kinetic energy acquired by alpha particle divided by kinetic energy of proton, which is equal to charge of alpha particle divided by charge of a proton into mass of proton divided by mass of alpha particle. Charge of alpha particle is 2q whole square. Charge of proton is q into mass of proton is m. Mass of alpha particle is 4m. These two will get cancelled. Q, it's going to be q square, right? Okay. So this q square will get cancelled. We are going to, I think 4 also will get cancelled. Then kinetic energy of alpha particle is the same as kinetic energy of proton. So what is kinetic energy of proton? It's 1 mega electron volt. So answer is 1 mega electron volt. There is no any change. So answer is same. Okay, let's move on to next question. Question number 14. A proton carrying 1 mega electron volt kinetic energy is moving in a circular path of radius capital in uniform magnetic field. What should be the energy of alpha particle to describe a circle of same radius in the same field? Just now we solved that for question number 14. What's the answer? Question number 13 and 14 both are same. Let's try another one. Under the influence of a uniform magnetic field, a charged particle moves with a constant velocity v in a circle of radius capital. The time period of rotation of the particle. First of all, let me write down the formula for time period. So 16th. As I know the radius, so here it is. Just now I've given here, this is velocity and radius is r. How to find out time period? Time period is equal to distance by velocity, right? Distance is total distance here, 2 pi r, total path length of the charged particle, divided by velocity is v. So 2 pi by v into, what is r here? R is mv by qb. This v will get cancelled, then it is going to be 2 pi m by qb. That is the time period. Does this time period depends on velocity of the charged particle? No, right? Okay, so on what parameters this time period depends, that's what we have to decide. So t is equal to 2 pi m divided by qb. Check out. First option depends on r and not on v. Is independent of both v and r. Next, depends on both v and r. Is there any r and v variables here? No. So it is completely independent of both r and v. Understood? Okay, let's solve next question. 17th. A particle of mass m, charge capital Q and kinetic energy T enters in a transverse uniform magnetic field of B. After 3 seconds, the kinetic energy of the particle will be, remains the same. Kinetic energy of the particle does not change here. So why it is remains the same? Let us see. Observe this circular path. Whenever a particle is moving in a circular path like this, a magnetic force is acting towards the center. Does this magnetic force changes the speed, or will it changes the direction? As it is changing direction, if you observe position 1, 2, 3, 4, So v remains the same, but its direction is changing. So it's at position 1. Okay. So velocity, I'm representing it as v vector. V vector is vi cap. But what about magnitude? Magnitude of velocity is v only, right? Let me take case 4. What is velocity? Velocity is minus v j cap. But what about direction? Magnitude of velocity, which is equal to v. See, magnitude of velocity is nothing but speed. Is speed is changing? No, speed is constant. What about kinetic energy? Kinetic energy is 1 by 2 m v square. So this v is speed or velocity? Speed. So as the speed is constant, then kinetic energy of that particle is also remains constant as it is. That is the reason here. So what's the answer for this 17? So as kinetic energy initial it is T, final kinetic energy also T itself. It does not change. Got it? Next, question number 17. Sorry, question number 16 completed, no? Question number, this is 15. Okay, it is 16. Next, question number 17. Let's answer that. A charged particle moves through a magnetic field in a direction perpendicular to it. Definitely it will undergo a circular path. Then speed of the particle remains unchanged. Yes, it is. Which option? Option A is correct. Just now I told you speed remains constant. Next, an electron having mass m and kinetic energy E enters in a uniform magnetic field B perpendicular. Then its frequency. Formula for frequency. Time period formula. Question number 18. Time period formula is 2 pi m by qb. Then what about frequency? Frequency is 1 by time period, which is equal to qb by 2 pi m. qb by 2 pi m. Option C is correct answer. Next, a charge having E by m is equal to 10 power 8 coulomb per kg and with a velocity 3 into 10 power 5 meter per second enters into a magnetic field B Tesla at an angle 30 degrees with the direction of field, the radius of curvature. Okay, super. So question number 19. So in this case you are going to get a helical path. Just observe here. This is magnetic field. Charged particle is entering at an angle 30 degrees with respect to electric field. Now you just have to divide this into two components. So horizontal component and vertical component. Horizontal component is v cos theta, vertical component is v sin theta. Okay, so because of these two components we have to find out magnetic force. Is there any magnetic force due to this? Magnetic force is equal to 0 because both are in the same direction, right? V cos theta and B both are in same direction, but because of V sin theta magnetic force will be present. What's the direction of magnetic force acting on the charged particle due to V sin theta? Use right hand palm rule. Thumb indicates direction of V sin theta, four fingers indicate direction of magnetic field, open palm indicates direction of force acting on it, which is into the board, Fm. So because of this V sin theta, charged particle undergoes a circular path, that is, so what's the value of radius? Radius is equal to mv sin theta. It's not only v, it is v sin theta divided by qb. Actually we are going to get a helical path like this. So this is the actual path of the charged particle in this case. This is how charged particle will move with a constant pitch because horizontal force is 0. Okay, so what's the mass ratio? E by m ratio is given, that is 10 power 8. Then m by e ratio, see m by q ratio is going to be 10 power minus 8. 10 power minus 8. Velocity is 3 into 10 power 5 meter per second sin 30 divided by magnetic field is 0.3. Okay. 10 power minus 8 into 10 power 5 is 10 power minus 3. This 10 denominator 10 power minus 1 goes to numerator. It will become 10 power plus 1. So finally it is going to be 10 power minus 2. 3 will get cancelled. So 1 by 2 into 10 power minus 2 is there, which is 0.5 centimeter. Option B is the correct answer for question number, sorry, let me cross check. Correct only. Option B is the correct answer for this. Okay, next, a positively charged particle moving due east. Okay, question number 20. A positively charged particle is moving towards east direction. Next, enters a region of uniform magnetic field directed vertically upward. Okay, so this is the direction of magnetic field. So this is the motion of the particle, that is velocity direction. This particle will, okay, if you just observe this angle between motion of the particle and magnetic field, both are perpendicular with each other, definitely this charged particle undergoes a circular path. Remember, it is always applicable. Undergoes circular path. Whenever a charged particle moves perpendicular to magnetic field, it will undergo a circular path. For question number 20, which option matches? Let's check it out. Option A, move in a circular path with decreased speed. No, it is not. Speed is constant in a circular path. Move in a circular path with a uniform speed. Option B is correct. Get deflected in vertical upward direction. No, it is not. Move in a circular path with an increased speed. No, it is not. So option B is correct. Next, question number 21. I told you reason earlier, just go through that. A 10 electron volt electron is circulating in a plane at right angles to uniform field at magnetic induction 10 power minus 4 Weber per meter square. The orbital radius of the electron. Okay, so they are asking radius in terms of energy. Our formula is root of 2mke divided by qb. So this is what the formula. I just substituted those values. Then you are going to get approximately answer. It is as 11 centimeter. Which option matches here? Option A is the correct answer for this. Let's move on to the next question number 22. What's the question? A uniform magnetic field acts right angles to the direction of motion of the electrons. And in which path the particle will move? Circular path. As a result, the electron moves in a circular path of radius 2 centimeter. They have already given radius is equal to 2 centimeter. Okay. If the speed of the electrons is doubled, then the radius of the circular path will be. So what about the formula for radius? R is equal to mv by qb, right? Does radius depends upon velocity? Yes, it does depends, because it is directly proportional to v, right? If velocity doubles, then what happens to radius also? Radius also doubles. What's the original radius? 2 centimeter. Now it will become 4 centimeter. That's all. Next, because it is directly proportional. Next, question number 23. A deuteron. What is the meaning of a deuteron? A proton and a neutron of kinetic energy 50 kilo electron volt is describing a circular orbit of radius 0.5 meters. So kinetic energy is given for the deuteron 50 kilo electron volt and the radius is 0.5 meter in a plane perpendicular to magnetic field. Okay. The kinetic energy of a proton that describes a circular orbit of radius 0.5 meter in the same plane in the same magnetic field. Super. So they just gave one proton and one deuteron. See, if you read, proton that describes a circular orbit of radius 0.5 meter. Deuteron radius is also 0.5 meter. Is radius is same or different? Radius is the same. First of all, let me write down formula for radius in terms of kinetic energy. R is equal to root of 2mke divided by qb, or else you can write down it is as square root of 2mke divided by q square b square. That is also another way to answer it. Now they said R is same. It's clearly mentioned R is same for both deuteron and proton. What about kinetic energy? The kinetic energy of proton that describes a circular path of, we have to find out the kinetic energy of the proton because B is the same. Okay. Mass and kinetic energy changes, right? Mass, kinetic energy, charge also changes. Let's write down the relation between them. Here, From this we can change that. I think already we solved this kind of model. So Q is directly proportional to root of m ke, and kinetic energy is directly proportional to q square by m. I need kinetic energy of a proton. Kinetic energy of proton divided by kinetic energy of deuteron, which is equal to charge of proton divided by charge of deuteron whole square into mass of deuteron divided by mass of proton. Charge of proton is q. Charge of deuteron is also q because it consists of one proton, one neutron. Neutron is not having any charge. Whole square into mass of deuteron is 2m because one proton mass, one neutron mass. Mass of proton is m. Mm will get cancelled. This q will get cancelled out. So you are going to get 2. So kinetic energy of proton is equal to 2 times of kinetic energy of deuteron. What's the kinetic energy of deuteron? 50 kilo electron volt. So it's going to be 2 into 50 kilo electron volt, which is equal to 100 kilo electron volt. Option D is the correct answer for question number 23. Got it? That's the way to answer. Next two numericals are based on the combination of both electric and magnetic field. Let's solve them. Now question number 24. An alternating electric field of frequency f is applied across the Ds of a cyclotron that is being used to accelerate protons. The operating magnetic field B is used in the cyclotron and the kinetic energy K of proton B produced by it is given by. So this is again same. So this accelerated proton is moving perpendicular to the magnetic field, so it is undergoing a circular path. In that case, frequency of the charged particle is going to be same as earlier case, that is q b divided by 2 pi m. So from this, what's the magnetic field? B is equal to 2 pi m into f divided by qb. Okay, so which option matches here? Sorry, q alone. That q is replaced with e here, and this one is replaced with a nu. Okay, so which option matches? See, option B and option C both looks like similar. We have to select which one of this. Okay, that means we have to find out kinetic energy. So in this case, as charged particle is moving in a circular path, centripetal force is nothing but a magnetic force. So magnetic force is equal to centripetal force in this case because particle is moving in a circular path. Magnetic force is q v b. Centripetal force is m v square by 2. So from this, not mv square by 2, it's mv square by r. Okay, mv square by r. What should we have to find out? Kinetic energy, right? So from this, mv square is equal to q r v b. What's b here? 2 pi m into f divided by q. This q will get cancelled out. Then this is mv square. Then what about kinetic energy? Kinetic energy is equal to 1 by 2 mv square, right? Then it is 1 by 2 into r into v into 2 into pi m f. This 2 also will get cancelled. Then kinetic energy is equal to, final answer, it's just made a small mistake here, just a small calculation mistake. Just observe here. Here one v will get cancelled, right? This v will get cancelled. Then what about v here? V is equal to q b r divided by m. Then kinetic energy is equal to 1 by 2 m v square. 1 by 2 m v square is q square b square r square by m square, right? 1 by 2 m will get cancelled. Then 1 by m into q square r square. What is b square? Let me substitute this. It's going to be 4 pi square m square f square divided by q square. This q will get cancelled. 1 m will get cancelled. 2 1s are 2 2s are. So final answer 2 pi square m r square f square. So which option? Option C is the correct answer for this question. Got it? That's the way to answer. Understood? Next. Question number 25. Let's solve the next question. A particle having a mass of 10 power minus 2 kg, m is equal to 10 power minus 2 kg. Then charge q is equal to 5 into 10 power minus 8 coulomb. Okay. The particle is given initial horizontal velocity v is equal to 10 power 5 meter per second in the presence of electric field and magnetic field to keep the particle moving along horizontal direction. Okay, so let's imagine. So I think I already told you this. If electric field and magnetic field both are in same direction, and if I project this charged particle in the direction of these two, electric field and magnetic field, electric field on this charged particle is not equal to 0, because whatever it may, whether it is in the same direction or opposite direction of motion, definitely electric force will be present. What about magnetic force? Magnetic force is equal to 0 because charge is moving in the direction of magnetic field. That is QVB sine theta, right? Theta is equal to 0 here, so that's why it's going to be 0. Magnetic force is 0. Magnetic force acting on the charged particle is 0, but electric force acting on the charged particle is non-zero. In this case, this charged particle will move along the same horizontal direction, horizontal motion. Is there any possibility of another motion? No, it undergoes only horizontal motion. So let's check out the option. B should be perpendicular to the direction of velocity. No, it is not. If it is perpendicular, particle undergoes a circular motion. Next, B and E should be along the direction of velocity. Okay, yes, it is possible. The second option is possible. Next, both B bar and E bar mutually perpendicular and perpendicular to the direction of velocity. This is also possible. So which option? Option C is the correct answer for me. Okay. So this case you can answer with the help of direction. You just take magnetic field. So let me explain you that also so that you will get a clarity on it. Let's imagine electric field is upward and magnetic field is into the board. Velocity of the particle is towards right. Now tell me, is these two are perpendicular with each other? Yes, they are perpendicular with each other. Now tell me, what's the direction of electric force acting on this charge? Electric force is always in the direction of electric field. Okay, what about magnetic force? Magnetic force direction can be calculated with the help of right hand palm rule. 4 fingers indicate direction of magnetic field, thumb indicates direction of motion of the charged particle. Then here in this case magnetic force is upward direction only. So as magnetic force and electric force both are in same direction, charged particle doesn't tilt, it will move along the same horizontal direction only. Okay, so that means it will move in the same straight line. That's the meaning here. Got it? Next question number. So which option is correct for this case? Question number 25. Option C. Next, a beam of electron passes undeflected through mutually perpendicular electric and magnetic fields. If electric field is switched off and the same magnetic field is maintained, the electrons will move. Okay, super. Question number 26. This case is possible only here it is. A beam of electron is passing undeflected. That means electric force and magnetic force both must be in opposite direction to each other. Okay, to produce like this. So we are producing an electron beam, right? So imagine electron is moving towards right. That means what's the direction of motion of a positive charge? Towards left. To get magnetic force downward, what should be the direction of magnetic field? Use right hand palm rule. So this is velocity of the conductor and force is towards down, then definitely magnetic field must be into the board. Okay, and on this positive charge, to get direction of electric force is field is going to be definitely in the direction of electric field. Okay, so this is the direction of electric field. Now I got the answer. This is how, if these two forces are equal, then only this charge moves undeflected. So I am answering with respect to a positive charge. Understand? I'll repeat again. If a negative charge is moving towards right, definitely positive charge will move towards left. That's what our imagination should be. As I know velocity and magnetic force acting on the positive charge, we can find out magnetic field direction with the help of right hand palm rule. By using that, I found magnetic field direction into the board. Now, as this is a positive charge, electric field will be always in the direction of electric force. That's why I did represented electric force like this. Now what's they are doing? They are turning off electric force. Electric field is turned off, right? If electric field is turned off, we are having only magnetic field. Magnetic field is into the board, and the velocity of the charged particle, positive charge is moving towards left, negative charge is moving towards right. Then what happens is, this velocity is perpendicular to magnetic field. Yes, it is. Then what kind of path that charged particle undergoes? Definitely a circular path. Question number 26, answer A is correct. Understood? Be careful with this analysis. Hope you understand. If not, go through it again and again. Next question number 27. If a mass of spectrometer used for measuring masses of ions, the ions are initially accelerated by an electric potential V and then made to describe a semicircular paths of radius Kepler using magnetic field. If V and B are kept constant, the ratio of charge on the ion by mass of the ion will be proportional to. Okay. So it's like you are giving some potential, right? Whenever potential given, the charges will displace us. That means the charges gains kinetic energy. So whatever the kinetic energy gained by those charges is from potential only, right? So QV is the work done to displace the charge, which is converted into kinetic energy. That is 1 by 2 mv square. Okay. So where m is the mass of the ion, q is the charge of the ion here. Understood? Similarly, so this charge will undergo a circular path, right? So we know that magnetic force is equal to centripetal force. So what's magnetic force? Magnetic force is QVB, which is equal to mv square by r. From this we will get cancelled. What is V here? V is equal to QBR divided by m, right? See, substitute this value here. Let's see what we are going to get. QV. V is the potential here. And this V is velocity or speed. Okay. So this is potential. Understand the difference between them. So let me substitute them. 1 by 2 m. V square is Q square, B square and R square by m. Q will get cancelled. From this I need a Q by m ratio, right? So Q by m is, if you send this R square to denominator here, it is inversely proportional to R square, right? So which option matches? Option A is the correct answer for question number 27. Got it? Let's move on to the next question. In Thomson's mass spectrograph, electric field and magnetic field perpendicular to magnetic field, then the velocity of the electron beam. Okay. In this case, force due to electric field and magnetic field both are equal. That is, magnetic force is equal to electric force. Magnetic force, I'm talking about only magnitude, it is QVB is equal to, what do you call this one? Q into E, right? This will get cancelled. Then V is equal to E by B. So this is magnet. This one again can be replaced as magnitude of E vector divided by magnitude of P vector. Which option matches? Option A is the right answer for question number 28. Let's move on to question number 29. Hope you are following. A beam of electrons is moving with a velocity, constant velocity, in a region having electric and magnetic fields of strength 20 volt per meter and 0.5 Tesla at right angles to the direction of motion of the electrons. So what is the velocity of the electrons? Just now we have the formula, right? So how to decide it? It's going to be V is equal to E by B. What's the value of E? E is 20, B is 0.5, which is equal to 40 meter per second. Okay, which option? Option D is the correct answer. Next topic is Biot-Savart's law. So we need vector form of Biot-Savart's law. We know the formula. It's a direct question. They're asking Biot-Savart's law vector form. Vector form is mu naught I by 4 pi dl bar cross r bar by r cube. Option B is the correct answer. Understood? If it is magnitude, you are going to get mu naught I dl sin theta by 4 pi r square. That's all. Okay. So let's solve numericals based on magnetic field on the axis of a circular current carrying loop. Before solving this numericals, I would like to give one note based on this. The note is, if I have a curved wire which is carrying current I, then magnetic field at the center of this curved wire, let's say radius of this is A, and this point I have to find out magnetic field. You just observe, I told you already, if this is the direction of current, you just have to cross check this point whether it is right side or left side of the current direction. As it is a right side, then magnetic field is going to be into the board. If it is left side, out of the board. Nothing but right side inwards, left side outward. You can use right hand thumb rule also. Thumb indicates direction of current, curled fingers indicate direction of magnetic field. Okay, so here as this point is right side of current direction, the magnetic field is going to be inwards here. Understood? Okay, so if the angle is theta, I have a direct formula for this, that is magnetic field is equal to, at the center, mu naught I by 4 pi A into theta. See, theta I can substitute based on the value. So for example, if theta is equal to 2 pi, that means complete circle, then magnetic field is equal to mu naught I by, if you substitute 2 pi, it's going to be 2A. This is magnetic field at the center of a current carrying circular coil. This is due to some complete circle, magnetic field due to a current carrying circular coil at this center. Okay, so if theta is whatever the value, you can substitute based on the given condition. Okay, now observe this question. Question number 31. So as current is entering here, it's going to divide here, it is as I1 and I2, and it is going to leave at this point as I itself. Okay, so let's say length of this is L1 and this is L2. Let me use current division rule. So I1 is equal to I into opposite resistance or same resistance, opposite resistance, R2 divided by R1 plus R2. If you observe these two wires looks like as if they are connected in parallel with respect to these points. This is one resistor and this is one resistor. These two looks like as if they are connected in parallel. That's the reason I am taking current division. So what about I2 formula? I2 is equal to I into R1 by R1 plus R2. Let me divide both of them. So it's going to be I1 by I2 is equal to R2 by R1, right? Which can be replaced as, if you observe length is getting changed here. So here R2 is equal to rho L2 by A. Here A divided by rho L1. A will get cancelled. Then I1 by I2 is equal to L2 by L1, right? Okay, so how can I calculate L1? Total length is 2 pi r. For 2 pi complete 2 pi r, length is L. Then for, instead of this, let me give you one more shortcut. For 2 pi angle, what's the length? Let's say L. And for this is pi by 2 and this is 3 pi by 2. So for 3 pi by 2, what's the length? It's L1. So L1 formula, 3 pi by 2 divided by 2 pi into L. Pi will get cancelled. It's going to be 3 by 4 times of L. Similarly, for 2 pi length, L, for 2 pi angle, length is L. For pi by 2, what's going to be length? That is L2. And L2 is equal to pi by 2 divided by 2 pi. Pi will get cancelled. You are going to get 1 by 4 times of L. This is L2 and L1. Let me substitute here. I1 divided by I2 is equal to L2 is 1 by 4 times of L. 3 by 4 times of L is L1. L by 4 will get cancelled. You are going to get 1 by 3. So I2 is equal to 3 times of I1. Okay, now let's find out the answer. So observe current direction. For this current direction, this point is right side or left side? For I1 I am talking about. For I1, this point is right side or left side? Right side. So magnetic field is going to be into. Now observe this for this current direction, and the point is left side or right side? Left side. So magnetic field is going to be out of the board. Let's say this is B1 and this is B2. Let me substitute that. So as these two are in opposite direction, we have to subtract them. B1 is mu naught I by 4 pi, what's the radius? Did they give radius? Radius R, 4 pi R into, what's the angle for B1? It's going to be 3 pi by 2, right? So it can be replaced with pi will get cancelled. It's going to be 3 times of mu naught I1 divided by 8R. This is B1. What about B2? B2 is equal to mu naught I2 by 4 pi R into pi by 2. Pi will get cancelled. It's going to be mu naught I2 divided by 8 times of R. Which is greater? B1 is greater than B2. And what is the direction of B1? It's into inwards. B2 is outwards. So B net is equal to B1 minus B2, which is equal to 3 times of mu naught by, do one thing, try to bring out which is common. Mu naught by 8R is common. 3I1 minus I2. So what's the value of I2? I2 is equal to 3 times of I1, right? So answer is going to be 0. Which option? Option A is the correct answer. Got it?